In this video, we're going to be looking at a starred problem in Broverman 1.4.9, which means it's not an old exam question. It's a more in-depth question, and in fact, this is a pretty theoretical question. I think it's still worth doing, though. You still should strive to understand things, and sometimes doing some theory is the best way to understand things and review some skills that you might need. It's a mathematical verification that when you compound more often, you get higher growth, and also in the limit, as the number of compounding periods goes to infinity, we call that continuous growth. You get the number e involved. We want to see that happen. Calculus is required to understand this video, but you need calculus to understand exam 2 anyway, so it's good to start somewhere. Here's the problem. Actually, it's parts A and C, I should say, of problem 1.4.9. There was a part B and D, but that would make for a really long video. I decided to just do parts A and C. So we want to show that if you've got a fixed J that's positive, J is going to represent your interest rate, your nominal annual interest rate, say, then this function, it's a function of M for fixed J, is increasing. It's an increasing function of M. Typically, we are, in doing compound interest problems, thinking of M as being a discrete variable, 1, 2, 3, 4, 5, 6, etc. But in order to use the techniques of calculus, we're going to go ahead and assume M as a continuously varying variable. And then in the second part, we're going to use L'Hopital's rule to show that in the limit, as M goes to infinity, the value of f of M approaches e to the j power, which corresponds to continuous growth. All right, so get your calculus skills ready here. Let's do this in a series of steps. The first step I'm going to write down is technically not necessary as far as what the problem statement is asking for, but I'm going to need it later on here. So I'm just going to note that certainly f of m is a positive quantity. Okay, look at that equation for f of m. J is positive. This is an exponential thing. It's going to be a positive quantity. There's no negative signs in there. So that's positive. We're going to need that in a minute here. The second thing we want to do then, to show this is an increasing function, think about your calculus, you want to show its derivative, thinking of m as a continuous variable, is positive. But what would the derivative of that thing be? That's a little bit tricky here. You might be looking at this and saying, what kind of function of m is that? Is it a power function? Is it an exponential function? It's actually neither, though it's, I'd say, closer to an exponential function. You've got an m up there, that's your variable, but you also have an m inside. There's no clear way to differentiate this. However, I will tell you that in these kinds of situations, it's often a good idea to differentiate not the function itself, but its logarithm, its natural logarithm. Oops, this is an m here. I'm going to differentiate the natural log of this function and use the property that with a natural log of a quantity like this, you can take the exponent and bring it down in front. So the logarithm of this function equals m times the natural log of 1 plus j over m. And differentiate both sides of this with respect to m. And that's definitely doable now over here. This is a function where it's more clear how to differentiate it with respect to m. But you do have to be careful when you differentiate the left side, excuse me, d dm here. This is a composition, natural log of f of m. Again, that's an m there. You've got to use the chain rule. The derivative of natural log of x is 1 over x, so we get 1 over f of m here. But then I need to also multiply times the derivative of the inside function. That's just f prime of m. I'm going to be able to solve this equation ultimately for f prime of m. Sometimes people use y in here in place of f of m, and they write 1 over y times dy dm. It's not a big deal either way. We can differentiate the right side as well, use the product rule. The derivative of m with respect to m is 1. That's the derivative of the first function times the second function, plus the first function times the derivative of the second function, this natural log here, which I'll need the chain rule for again. Once again, the derivative of natural log of x is 1 over x, so I get 1 over 1 plus j over m. But now I need to multiply times the derivative of the inside function here with respect to m. The derivative of 1 is 0, the derivative of j over m, I hope you can quickly calculate to be negative j over m squared. All right, let's see. think it's helpful to do a little bit of simplification here. For example, this m can cancel with, say, one of those. I'm also going to bring the negative j over m up into the top and maybe the negative sign out in front. I'm going to write this derivative. Well, now actually I'm going to multiply both sides by f of m. So f prime of m is f of m, which is the original function, times this whole thing here. I'll put it in parentheses like this. I think we may need 2 pages for this video. Let's see here. I'm going to have to try to write small. Hopefully I don't make a mistake. I think everything looks good here. So there we have the derivative of f with respect to m. Kind of nasty. What is our goal with this? Our goal is to show it's positive, because if we can show it's positive for all positive values of m, and j is a fixed positive number, that will mean the original function is an increasing function of m. Looks kind of difficult. This is definitely positive. That's by observation 1. There we used it. So the key thing is to show, is this positive? I'll put greater than 0 question mark. Is that positive? Since m is occurring in kind of a, in the denominators here, it turns out to be helpful to, let's give this function a name, but let's call it h of x. Let's replace the j over m with x to make it simpler looking. Like that. I feel like I need to double check to make sure there are still no mistakes here. I think we're okay. If we're not okay, I guess I'll make a new video or something. If I can show this function is positive when x is positive, that will mean this function is positive as well. Do note that h of 0 is natural log of 1 minus 0 is 0. If I can show h prime is positive, that will then mean h itself is positive when x is positive. Do you understand that? Since h of 0 is 0, if you were going to graph this function of x, its graph goes through the origin. If I can show its derivative is positive for all positive x, that will mean this function's increasing, so it's got to be positive when x is positive. So we take another derivative here, lots of calculus. There we took the derivative of natural log of 1 plus x. Then with this one, I guess we'll use the quotient rule. Low d high minus high d low over the square of what's below. That's how I remember the quotient rule. Let's see, what does this simplify to? The x's cancel on top. It looks like I've got this. Again, hopefully no mistakes. Get a common denominator of 1 plus x squared. It looks to me like this is the case. This is what I get. And lo and behold, this thing is positive if x is positive, which is what I wanted. Okay? Again, that's going to mean h is an increasing function of x when x is positive, and since h of 0 was 0, the graph has got to go upwards away from the origin as x increases. It's got to be positive. That's the key thing. H of x is positive. Therefore, this question mark back up here is no longer a question mark. It is true. This thing is positive, so f prime of m is positive. It's positive times a positive, meaning that f is an increasing function of m, back in the original question. Okay? All right, how long are we going here? We're almost at 9 minutes. All right, I think we got to keep going. Let's try to go quicker on the second part. Use L'Hopital's rule to verify that this limit is true. I'm taking the limit of this function f of m as m goes to infinity. Let me write the formula for f of m again. Once again, it's not clear how to use L'Hopital's rule with this. Once again, it's helpful to take the natural log of both sides, just like we did in the first part. Once again, using the property of logarithms, allowing me to write the right side like this. And it turns out to be easier to apply L'Hopital's rule to this. If I write this function in the following form, do a little trick. Natural log of 1 plus j over m, all divided by j over m. Oh, no, excuse me, all divided by 1 over m. These two things are the same, as long as m is not 0, and it's not, it's positive. Take the limit of this with L'Hopital's rule. as m goes to infinity, assuming m is a continuous variable, and then ultimately exponentiate to get back to the limit of the original thing. So let me just go ahead and write limit as m goes to infinity, natural log of 1 plus j over m over 1 over m. This is, it should be checked, an indeterminate form. As m goes to infinity, this thing goes to 0, and so does this thing. J over m goes to 0 as m goes to infinity. This thing inside the natural log goes to 1. Natural log of 1 is 0. This is a 0 over 0 indeterminate form. That should always be checked before you apply L'Hopital's rule. So then L'Hopital's rule says that if you differentiate the top and the bottom individually, not the quotient rule, but individually, and create a new fraction that's the ratio of those derivatives, and if that limit exists and equals something, then this limit will be the same thing and equal that same thing. What is the derivative of the top? Once again, we use the chain rule. Once again, I get a negative j over m squared in here. Differentiate the bottom, I get a negative 1 over m squared. And we might think, okay, do I have to use L'Hopital's rule again? No, don't use it again. Simplify. The negative signs cancel, the m squareds cancel. We get the limit as m goes to infinity. Let's see, it looks to be negative, oh no negative sign, positive j over 1 plus j over m. And that quantity definitely has a limit as m goes to infinity. This goes to 0. This approaches j as m goes to infinity. That is that limit. Now exponentiate to get back to the limit of the original function as m goes to infinity is going to be e to the j. Let's see, okay, let's just go ahead and write that. Since the limit of the logarithm of the function is j, the limit of the original function is e to the j. Technically, we're using the continuity of the logarithm function to do that, and the exponential function, say. If you want it, maybe I should show more detail here. If you wanted a little bit of extra justification for this, you could write it this way. Using the fact that the natural log of x and e to the x are inverse functions, then I can use the continuity of e to the x to bring the limit sign up into the exponent. And from what I just did, that limit up in the exponent is j, so this becomes e to the j. Okay, so again, this equals that because of inverse functions, this equals that because of the continuity of e to the x, and this limit we already found was j, so the answer is e to the j, and that does it. Thanks for watching. I realized after stopping the video that I really should have said a little bit more, even though the video was long. We get e to the j here. I should really relate this to continuous compounding. The expression e to the j times t, say, represents continuous compounding at continuous rate j over time, and when time is 1, this would equal e to the j, and that would be what $1, say, would grow to in 1 year. This is how much $1 or one amount of money would grow to in 1 year under compound interest, compounded m times per year, letting m go to infinity, so it's like you're compounding all the time. It grows to e to the j. That is the basis of continuous compounding. If you don't deposit 1 but some other amount, you'd put the other amount in front of this. Again, thanks for watching.